Okay, so for this super lively audience today, we're going to talk about return-oriented programming, um, which, like, based on popularity of most exploits, the ROP is involved like a significant amount of the time, and so there's like a lot of um, predicated knowledge on ROP that can like help you trampoline into some other exploits. And since it's Temple of Pwn, which is TOP, then this is ROP top, which sounds like crop top. So
Ah,
little crop top. Uh, was hoping for some big laughs there, but that's okay. We'll just move on. Okay, so what is this? So security implementations like NX and DEP were actually a pretty big detriment to the exploit community. So like it's really popular to just write your own shellcode, put it wherever you wanted in memory, and then jump to it. Um, but that's not always very possible. And in places like Windows and Linux, you could still like ret into libc and well in Windows you could virtual alloc and like reset permissions on pages of memory. And in Linux you can do the same thing if you go like into brk and you can like remap pages so they're executable. But like that can be pretty difficult because like you have to manage to then return back into the place where you're going into. So maybe maybe there's a limitation on your execution flow. And so NX and DEP were like pretty solid. But if we some researchers, I don't even know when Rob came out, but thought, no, maybe there's actually small amounts of already executable page space that we could manipulate like one at a time. Like maybe there's these subroutines that contain an instruction we care about, maybe instructions we don't care about, and then a return. Or maybe just instruction we care about, nothing, and then a return. And then we can kind of stack these on top of each other and like create our own function that if you were to replace the rets with nothing, maybe the function would have flow that you would maybe write yourself. And so like right here, maybe there's a way to perform a lot of small desirable operations. So like maybe these mini subroutines called gadgets could contain everything that we might need um, if we were to write our shellcode without the rets. So why I we already talked about this. NX and DEP are annoying. Um, this like ROP can be disabled by other things too, like a canary, and no way to leak the canary or brute the canary would stop ROP too because we need to control RIP. But for the most part, the big reason that ROP is implemented is because DEP, I mean, stopped the ability even if you were able to write to your own shellcode. And so this is just like the one for one defense versus over like overloaded attack. So like if NX is enabled, nothing else, like it's probably pointing to ROP being a probable exploit path. Okay, so how do we do it? The two biggest things you have to understand is what your stack space looks like. So I mean, what's our input buffer size? How much would we have to overwrite? Is there a canary we actually care about? Past the canary, how many gadgets can we hit? Can we actually get null bytes to return into those gadgets? Like, can we actually write null bytes into the stack, or are we maybe using a input function that's going to stop on null byte read? And then you also have to know your gadgets. Like, there's lots of tools that I'll show off here that will help you find your gadgets, but you have to know what they're doing because sometimes there's gadgets that are like dereferencing RAX and then moving in whatever's dereferenced. RAX is going to have a pointer to something that you can dereference because if you don't, then you'll get a seg fault instantly and everything will crash. Or maybe like it's doing a jump RAX and jump RAX still pointing to a page that isn't executable. Then you'll get like either a page fault or a seg fault too. So both of those can be like you've got to understand what your gadgets are doing. Even if they've got the instructions that you care about, they might have excess instructions that are bad. And then finally get a shell. Like there's lots of ways to do this. Maybe you don't even need to get a shell if there's a way that you can ROP into a syscall that opens your file and then reads and writes it. Or maybe the point of this isn't even to get a shell at all, but to just do some um, other reconnaissance before you move into the shell zone. And then there's tons of ways. We're just going to go through a single example. I think that's all for the slides. Yeah, that sounds good. Um, okay, so I went to just a really simple. I think I just CACTF um, easy ROP. Oh wait, actually, I think I can find it based on my netcat. I just went to a CTF that's like continually going to find a challenge. And okay, pwnable hackable. I think it's just hackable.ca. And then I just went to challenges and found easy ROP. And so I basically just pulled this challenge down and like started it this morning and thought it pretty closely represented what I think a pretty simple ROP challenge would be. So we pull it down, we check file on ROP. Okay, three things that are pretty important. First, unstripped. So like we've got function names or label names still in the compiled binary, so it's really simple to like find functions that we care about. 32-bit, so any instruction or any gadget that we're looking for, we've got to make sure we look for the 32-bit version. And if we're looking at a syscall table, we've got to make sure that we find syscall like values that are for 32-bit and 32-bit architectures. And then finally, we see that the binary is statically linked, which is actually like not that surprising since there's so many gadgets within libc functions that I'm guessing they wanted to keep ASLR on, um, which I guess they didn't really even do that. But like this is really simple. Since libc is probably going to be ASLR enabled, then you'd have to get some sort of memory leak to find the gadgets there. Instead, they thought, like, let's just put all of the gadgets in the base binary memory location, so then you can just like always predict where those gadgets are, which makes a lot of sense because there's so many gadgets within libc that this makes sense, and there's a ton of libc functions that are statically linked in. Okay, so in the slides, I talked about understanding your stack space. So let's first do some like preliminary reversing, see if we can figure out exactly how much we're reading in and how much space we've got to work with. And then we'll start looking for functions or looking for the gadgets we care about. So everything is non-stripped. So we can just look for main and find it here. Looks like it puts out some sort of character pointer. I think if we run it, it just says like user input, try running binsh. This is actually really cool too. So they give us a pointer to binsh or like binsh in the data section that won't change every execution. So that's really nice of them. Like hats off to them for being that generous. And then it just has input. We could probably like smash this and get some sort of seg fault. But we can go in and be a little bit more meticulous. So we've
Is
got a
there a
function
way
called
to increase the font size in Ghidra?
um I still don't know how to do that. So this is a really good time to figure out how to do that, I think. Uh, I know it's not in configure because that configure does totally different things. Let's go to the internet. Change font size Ghidra. That's not what you want to find. Um, that's not what I want either. Can we just straight zoom? No. There's got to be a way to do this, right? Uh, hmm. Can you not see it very well? Let's increase quality. Is it better now?
It's a bit better. Try
Okay.
edit, tools options, listing display.
Edit, tools options, listing display. Holy cow. Look at this. How'd you do that?
I googled it.
I couldn't even figure that out with Googling it.
You
Okay.
click the
Do I,
first issue that says unchangeable and it tells you how.
oh, should I go bigger? That's what she said.
That's up to you.
It's not zooming over here though.
Oh gosh.
I mean, this is pretty good though, right?
Yep. That's pretty good.
I mean, okay. Okay, anyway, so call Smash Me, which um, basically um, like sets this character pointer for the printf, then cleans up the stack, then moves in the character pointer for your buffer, which is right here, and then calls gets. So we basically have no limit from start of input to a new line. We could just read as much as we want. So like when I was saying know your stack, we don't have any limitations that we need to care about here. Um, Second, we can look at like how many bytes we want to actually read. So the variable array buffer is of size 8 bytes. Then we've got the old EBP that we're holding on to, and then the return after that. So we've got like 16 bytes that we need to overwrite, and then we've got like the first thing that we can write where we return to. So here I'll start making all these notes in the exploit. So we've got like our buff, we'll just say padding is equal to our A. We've got 16 bytes of that. And then whatever after that is going to be like our first ret. And this is where we're going to start defining some of those gadgets. So you've got like two kind of like main paths of ROP execution. There's a whole lot more, but like two simple paths would be one, I set up like maybe RAX, or sorry, set up like RDI and RDX, RCX, and some like this is for if we're in 64-bit. So 64-bit, we set up the registers that you pass parameters to add, we'll just say it, etc. And then return to libc system or execv. So this is like pretty standard, not really like that ROP intensive, but you'll ret to a pop RDI ret, and this is where you can like start to set up those registers before you get there. But we're not in 64-bit, we're in 32-bit, so maybe what we would do is set up stack to be something like the return location for system/execv, and then a like kind of just empty stuff because it doesn't really matter. And then, or well, you could fill it with whatever you want, but then this could be our pointer to bin.sh because that's how parameters are passed. You've got like param for old thing, param, and then you've got what the prolog was setting up, so the old EBP, and then you've got your local vars. And so if we could ret with our stack set up, oops, like this, then that'd be really good too. And we wouldn't actually have to ROP at all because we can set up the stack however we want, and we could just have the pointer set here. So the only issue with that is that though this is statically linked, we actually don't have static references to things like system. So we go into here, we've got like sysinfo, sysconf, sysmalloc, but no system static link, which makes sense. Like you wouldn't want to just statically link system. That'd make the challenge too easy. And then we go to execv, and usually functions that aren't used won't statically link by default, but you could force static linking of other things. Then we see we don't have it here either. So that was like our first preliminary path where we could just do some ret to libc system, but that doesn't look like it's going to work because we're not going to dynamically link in a libc if there's no functions that we need to dynamically link. So system will probably not even be in the executing memory space. So instead, we could do something like set up registers for syscall. So we would need something like a pop RAX, a pop, oh, sorry, this is 32-bit, an EAX, pop EBX, pop ECX, pop EDX, and then get all of those values to be perfect for an execve or an execv syscall, and then return to like an int 0x80. And so basically what this would do is set up all of these parameters for what, like if we want to pass execution off from us to the operating system, then execute our syscall, and then have all of the parameters set up so that binsh is what's executed. So this seems like a little bit more appropriate for our situation, especially since things are statically linked. We're probably going to be able to find these sorts of gadgets lots of places. So we're going here. We're going to want something like a pop EAX. So let's find that address now. So I'm going to show off two tools. First, ROPR, and then a Ghidra script that's been in development for a little bit now. So we're looking for something like a pop EAX. Sorry. And everything's statically linked, so we're probably going to get like a huge amount of feedback. Okay, we got like way less than I thought we were going to get. But there's a lot here that we probably don't even care about. Like this is jumping and then dereferencing AX. Like that's not good. Um, this one's probably fine, but there's really like a lot of additional things we don't even need to pop. So let's simplify our search to just have ret. We can already see that it's here, but just to simplify our search, we get this super easy pop EAX ret. So we'll copy this bad boy right into here. Okay, next, and we can go to something like the Chromium OS docs. There used to be a way nicer document that had syscall like parameter tables ready, but I think it's been down for a little while now. But this one's fine. So we can find our exec VE call. We need EAX to be 0x0b. So I like to just make comments next to here of what the value we want to get into there is, because this will set up like when we actually build our payload, it'll be a lot easier. We also need to get into EBX or binsh path, and then we probably just want nulls into ECX and EDX. So the next tool that I'm going to show to find gadgets is within Ghidra. Super cool developer wrote this ROP finder gadget, ROP gadget finder, which basically you can feed it a string here. So let's say we want pop ECX and ret. Then you can feed it a maximum gap instruction count, which basically says like how many bytes between these two instructions are you going to allow? And what the script will do is compile the basically what it'll do. Let's say that you just had pop RDI ret. So this will compile down pop RDI, and then it'll give it a regular expression to say that it can have anywhere between 0 to 10 varying bytes, and then it will have ret. So it's basically building out a regular expression on compiled assembly instructions. And then this gap is like the amount of bytes you're allowing between. But then what it does after, like this could give you a lot of issues. So what it does after is it then disassembles the bytes found and confirms that these instructions are found verbatim. Because you could have something like pop RDI and then an instruction that has C3 within it. Like maybe you have a move EBX C3, 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 and maybe that has like, it has the byte C3 somewhere. And so that would be no good. So it reassembles or it disassembles the bytes that are found, confirms that the instructions are still found within. So we'll say we are okay with 2 bytes between. Then we look, we found 2 gadgets, one here and one here. And so that's pretty cool. The first one looked pretty cool because it has all of our remaining register parameters that we need to set, EDX, ECX, and EBX, and then it finishes with a ret. So this gadget's actually insane. And we could confirm that ROPR would have given us the same instruction by searching for pop EDX, pop ECX, pop, if you know how to spell, EBX ret. Okay, just kidding. Maybe I went in the wrong order. EDX, ECX, EBX. Okay, never mind. Maybe ROPR sucks. And this tool is just way cooler. Or maybe it's the way I'm spacing these that it's not okay with. I don't think that would be it, though. I don't know. Maybe. Oh, no, it did find it. Okay. Dang, I really was hoping mine was cooler. So we find this instruction. We can go back into our exploit. Sometimes I just say like pop DCB, and I know that that's EDX, ECX, EBX. Give it here. And then we want to know what we want in these places. So EDX, we want there to be 0. ECX, we want it to be 0. But then EBX, if we go back to our reference here, we see that we want EBX to be the pointer to the file we want to open and begin execution at. So let's find that string that we were looking for before, or that bin.sh that they provided us. You can go bin.sh, find it here, and then try running bin.sh. This is kind of an annoying way to view it because it's like you'd have to hover and count bytes off, but you can just change this data to be characters, and then we can find the offset of where it first occurs. Uh, Hello, can you give me this address? I'm guessing that it's 0x080 and then these 5 bytes. So that's what we're gonna guess because did that actually work? Okay, cool. Like I'm almost certain that this is probably the correct. That'd be no, it'd still be after this page. Okay, so we'd probably be fine. Okay, so then we can start to think about our chain after we get one more instruction. We want to find a syscall. So unfortunately, this tool doesn't work very well finding syscalls because in 32-bit, I don't think that Ghidra will often assemble it to syscall or will disassemble the syscall. It'll instead disassemble the int 0x80. And then another issue is that it doesn't like to assemble hex characters. So if we do int 0x80, it fails to assemble. So we have to convert that to an integer value, which is 128, and then try to find that. And we find 2 gadgets. So we got a 0x80 here, and we've got a 0x80 as the first instruction here. So let's just take one of these. Either will work because we don't need a ret after it. So we'll call this a syscall. That. Okay, we're ready to build our payload. So our payload is going to be our padding, which is basically that first amount of input we can put before we are messing with RIP. Then we want to put our pop EAX. We can do this in any order, doesn't really matter. And we have to start to pack this for the input to actually handle the bytes properly. And here we just want 0x0b. Then we can do the rest of these, DCB. And first is just 0, then 0 again. And then finally this instruction for this value here that has the bin.sh string. Okay. And then finally the final ret will be to our syscall. Okay. So we're going to say our process equals process./ROP easy. Then we're going to send this line and go interactive. And oh my goodness, first try, it's never happened. In the history of the world, never happened. So we can see we got our shell back. Interactive keeps us live. So let's try to do the remote version. I kept this netcat so that I knew what the ports were. We'll go into our exploit, change this P to be remote version. Oh my gosh, not first try. We were on fire. Somehow who am I isn't found? Oh. No way, that's crazy. Okay, but anyway, so we see that we can ls and then we can just cat this flag. You can steal a flag if you want, but I mean, no one's really doing the CTF actively, so that wouldn't be that cool. And we're good. Okay. That's pretty fast. Thank you. Are there any things I flew through that are a little complex? ROP is actually like one of the most straightforward and like I think it's one of the most easy to understand exploit methods. Like it can be complex to understand like good gadgets and to try to find them and to know where they're going to be at. But like once you start like building out the stack a few times, like I don't think it's actually that complicated. I think it just gets really understandable because the gadgets and then whatever the gadgets do, make sure the stack's ready to handle. And then the gadget's finished with a ret, so just put the next thing you want to ret to. Like you don't have to worry about prologues or epilogues. Like it's a really easy function to function method of exploitation. Like I think it's pretty easy. I think it's way harder to like set up the stack so that your parameters are like in the perfect order afterwards and then ret into libc. Like that's I feel like that's way more work. I think ROP is super straightforward.
I got a question.
Hmm.
In your exploit, how many gadgets did you use total?
Okay, yeah, we'll go into that. Let's open up exploit. So, okay, you could claim that we only use 2 gadgets because I don't know what the proper definition of the syscall would be. Like, I mean, I guess it's a subroutine that did what we wanted, but we didn't care where the execution returned afterwards because like execve will dump all the memory space, all the current execution memory space, and then load in the new process. So, like, I guess you could consider this a gadget, but really, these were our two big gadgets that we used, like that you could fully define as gadgets with reds.
All right, follow-up question.
Hmm.
Suppose that you only had space to send in 4 P32s. What would your attack plan be?
So you're saying after this padding?
Yep,
Okay, so we have our padding, and then we're able to do
16
4 here.
characters.
Um, so we could, so like our first maybe um a first naive attempt would be to or debug this and see if some of these registers are okay already. Like maybe for some reason EAX has 0x0b in it and you don't need to adjust it. That's probably not going to happen here. And maybe these things are fine and you don't need to adjust them, which it'd be crazy for EBX to be pointing to this. Like that'd be pretty whack. So instead, it might be more beneficial to set up some of these registers. So like let's say it's not being that nice to us and like none of these are set up to be correct, then I would consider setting some of them and then returning back to where this function starts because maybe these registers aren't being adjusted in the function itself. And so we can set EBX, return back to the top of the function, overwrite again, get into a new gadget that we want. And then in that gadget, we can set ECX, and then return back to the top of the function again. And we can actually disassemble and we can see, like if we go back to uh, um, Smash Me, like there's a lot of adjustment of EAX because EAX used for all sorts of things. And there's like this add EBX thing here. I don't even know why this. Oh, okay, because then it loads off of EBX. But it doesn't look like ECX is adjusted, and it doesn't look like EDX is adjusted. This is a new function down here. So maybe what we do is we don't do this one yet. Instead, we say first payload equal to our padding plus P32 of this. Like let's say we find a pop ECX ret. I mean, we for sure have an ECX EBX. But let's just say for here, we just want to pop ECX ret. Then we could just adjust our ECX to be what it needs, which it needs to be 0, which it honestly could be anyway. And then we could put the address of the smash me function again. That's another attempt. That's another idea. And then we can, like, in this case, it's difficult because I don't know how we'd be able to do EAX and EACX in one go. But like, you could also maybe ret, like, you'd probably have a ton of, like, when you did your leave, you'd have a ton of errors because you wouldn't reset this prologue, but maybe you could ret to an area where EBX isn't adjusted. So like EBX is messed with right here. And so maybe you, oh wait, we're not even in Smash Me. EBX is messed with right. Wait, was I even looking at this the first time? Yeah, okay, it is messed with right here and here. Like maybe you could just go into where you're reading. You could rep back to here if you've got like prologue set up fine. I feel like that would probably break some things though. And also EBX is being adjusted here anyway. Oh wait, but all that matters is the gadget after. So like if EAX was fine, oh, but it would definitely be broken here. I don't know, it'd be tough. Or you could find one gadget that lets you do all of these. Or maybe there's a gadget that can like XOR ECX with itself, and then we don't even need to put data afterwards. It'd really depend on your available gadgets. In this case, I don't know how you do it. Maybe you have more expertise and would know what gadgets that would help us, but it'd be tough just because uh, setting this many registers and having them all be incorrect might be pretty tough. Do you have any cooler ideas for the audience?
Maybe for a future day.
Okay. I don't know. I don't know if there's a real simple, cool approach that would, yeah, that this understanding that would be super doable. And
So
maybe you also find like a crazy gadget that just like moves into EAX0, ECX0, EDX0, RET, and then we would only have to pop into EBX technically, and then we could put this here and then RET, and that would take 4. That would only take 16 bytes. But that'd be pretty crazy. Or maybe there's like a way to do all those one by one. But again, there's too much manipulation of EX, EBX. You'd have to be way cooler than me to figure it out. Okay, any other inquiries?
So what would it look like when your stack space is limited?
So like let's say you had way more freedom, and like let's say it's exactly what Logan said and you've only got 32 bytes of input. So 16 are stolen by this padding.
No, I mean like what would stop you from putting in more than 32 bits? Like,
Oh, okay.
maybe
Let's say instead of gets, they had read,
oh, okay, I understand.
and then it said 32. And so you could only read into this buffer 32
Yeah,
bytes.
that makes sense.
And so that would really kill us. Or also, you can run into big issues. Like, let's say this pop EAX was actually at 0x080A 94A6. Well, that's a pain in the balls because, like, this. Oh, wait, it actually wouldn't be. Let's say it finished with 0A. Like, you can't actually put this byte onto the stack because gets is
Right.
going to stop reading it when you give it that byte. And so I'm sure that the challenge creator had to make certain that the way that they compiled left like actually achievable input spaces. Because this would cut off the reading and you wouldn't be able to put any more bytes in because gets would stop. And so similar things can happen if you can't put in null bytes, or if maybe it's doing git char one at a time or something silly. Then you'd have to change the way that you're thinking about these gadgets so that you don't have null bytes within them. Like if we can't do null bytes here in this pop EDX, ECX, EBX, maybe we need more like XOR ECX, ECX, or XOR EBX, EBX. um, so that we can, because all of these gadgets have no null bytes within them, because it's 4 bytes to build out the full address. So maybe there's ways to avoid the null bytes. I mean, you have to have a lot of creativity when building out shellcode strings too. So similar things apply here.
Oh yeah.
Okay, well, if there's nothing else, that's a brief introduction to ROP.